Any theory which explains the existence of the moon must naturally explain the following facts. The moon's low density, 3.3 g/cc, shows that it does not have a substantial iron core like the Earth does. Moon rocks contain few volatile substances, e.g. water, which implies extra baking of the lunar surface relative to that of Earth. The relative abundance of oxygen isotopes on Earth and on the Moon are identical, which suggests that the Earth and Moon formed at the same distance from the Sun. Hello and welcome to KYC News. Please don't forget to subscribe and hit the bell icon. Various theories had been proposed for the formation of the Moon. Below these theories are listed along with the reasons they have since been discounted. The fission theory. This theory proposes that the Moon was once part of the Earth and somehow separated from the Earth early in the history of the solar system. The present Pacific Ocean basin is the most popular site for the part of the Earth from which the Moon came. This theory was thought possible since the Moon's composition resembles that of the Earth's mantle, and a rapidly spinning Earth could have cast off the Moon from its outer layers. However, the present-day Earth-Moon system should contain fossil evidence of this rapid spin, and it does not. Also, this hypothesis does not have a natural explanation for the extra baking the lunar material has received. The capture theory. This theory proposes that the Moon was formed somewhere else in the solar system and was later captured by the gravitational field of the Earth. The Moon's different chemical composition could be explained if it formed elsewhere in the solar system. However, capture into the Moon's present orbit is very improbable. Something would have to slow it down by just the right amount at just the right time, and scientists are reluctant to believe in such fine-tuning. Also, this hypothesis does not have a natural explanation for the extra baking the lunar material has received. The condensation theory. This theory proposes that the Moon and the Earth condensed individually from the nebula that formed the solar system, with the Moon formed in orbit around the Earth. However, if the Moon formed in the vicinity of the Earth, it should have nearly the same composition. Specifically, it should possess a significant iron core, and it does not. Also, this hypothesis does not have a natural explanation for the extra baking the lunar material has received. There is one theory which remains to be discussed, and it is widely accepted today. The giant impactor theory, sometimes called the ejected ring theory. This theory proposes that a planetesimal, or small planet, the size of Mars struck the Earth just after the formation of the solar system, ejecting large volumes of heated material from the outer layers of both objects. A disk of orbiting material was formed, and this matter eventually stuck together to form the Moon in orbit around the Earth. This theory can explain why the Moon is made mostly of rock and how the rock was excessively heated. Furthermore, we see evidence in many places in the solar system that such collisions were common late in the formative stages of the solar system. This theory is discussed further below. More about the giant impactor theory. In the mid-1970s, scientists proposed the giant impact scenario for the formation of the Moon. The idea was that an off-center impact of a roughly Mars-sized body with a young Earth could provide Earth with its fast initial spin and eject enough debris into orbit to form the Moon. If the ejected material came primarily from the mantles of the Earth and the impactor, the lack of a sizable lunar core was easily understood, and the energy of the impact could account for the extra heating of lunar material required by analysis of lunar rock samples obtained by the Apollo astronauts. For nearly a decade, the giant impact theory was not believed by most scientists. However, in 1984, a conference devoted to lunar origin prompted a critical comparison of the existing theories. The giant impact theory emerged from this conference with nearly consensus support by scientists, enhanced by new models of planet formation that suggested large impacts were actually quite common events in the late stages of terrestrial planet formation. The basic idea is this: about 4.45 billion years ago, a young planet Earth, a mere 50 million years old at the time and not the solid object we know today, experienced the largest impact event of its history. Another planetary body with roughly the mass of Mars had formed nearby with an orbit that placed it on a collision course with Earth. When young Earth and this rogue body collided, the energy involved was 100 million times larger than the much later event believed to have wiped out the dinosaurs. The early giant collision destroyed the rogue body, likely vaporized the upper layers of Earth's mantle, and ejected large amounts of debris into Earth orbit. Our moon formed from this debris. There used to be a number of theories about how the moon was made, and it was one of the aims of the Apollo program to figure out how we got to have our moon, says Sarah. Prior to the Apollo mission research, there were 3 theories about how the moon formed. Capture theory suggests that the moon was a wandering body, like an asteroid, that formed elsewhere in the solar system and was captured by Earth's gravity as it passed nearby. In contrast, accretion theory suggested that the moon was created along with Earth and its formation. Finally, according to the fission scenario, Earth had been spinning so fast that some material broke away and began to orbit the planet. What is most widely accepted today is the giant impact theory. It proposes that the moon formed during a collision between the Earth and another small planet about the size of Mars. The debris from this impact collected in an orbit around Earth to form the moon. The Apollo missions brought back over 1/3 of a ton of rock and soil from the moon. When the Apollo rocks came back, they showed that the Earth and the moon have some remarkable chemical and isotopic similarities, suggesting that they have a linked history, says Sarah. If the moon had been created elsewhere and was captured by the Earth's gravity, we would expect its composition to be very different from the Earth's. If the moon was created at the same time, or broke off the Earth, then we would expect the type and proportion of minerals on the moon to be the same as on Earth. But they are slightly different. The minerals on the moon contain less water than similar terrestrial rocks. The moon is rich in material that forms quickly at a high temperature. In the 70s and 80s, there was a lot of debate, which led to an almost universal acceptance of the giant impact model. Lunar meteorites are also an important source of data for studying the origins of the moon. In some ways, meteorites can tell us more about the moon than Apollo samples because meteorites come from all over the surface of the moon, adds Sarah, while Apollo samples come from just one place near the equator on the near side of the moon. Earth's greatest spin-off. Before Earth and the moon, there were Proto-Earth and Theia, a roughly Mars-sized planet. The giant impact model suggests that at some point in Earth's very early history, these two bodies collided. During this massive collision, nearly all of Earth and Theia melted and reformed as one body, with a small part of the new mass spinning off to become the moon as we know it. Scientists have experimented with modeling the impact, changing the size of Theia to test what happens at different sizes and impact angles, trying to get the nearest possible match. People are now tending to gravitate towards the idea that early Earth and Theia were made of almost exactly the same materials to begin with, as they were within the same neighborhood as the solar system was forming, explains Sarah. If the two bodies had come from the same place and were made of similar stuff to begin with, this would also explain how similar their composition is. The mineralogy of Earth and the moon are so close that it's possible to observe moon-like landscapes without jetting off into space. If you look at the lunar surface, it looks pale gray with dark splotches, Sarah says. The pale gray is a rock called anorthosite. It forms as molten rock cools down and lighter materials float to the top, and the dark areas are another rock type called basalt.